Okay, so today I'm going to be continuing with my series of videos on the Oxbridge interview process. And this is going to be the second video on implicit differentiation. In this video, I'd like you to think about how you might draw the graph of y equals x to the x. Okay, so x to the power of x. Let's put some axes down so we can think about this. Okay, so y-axis and an x-axis. And most of the time when I give students this question, they usually say, oh, well, this will be an increasing function, it will never go negative, and it's going to look something like e to the x. Okay, not quite right. So we need to first think about what happens at x equals 0. So x equals 0, this is 0 over 0. Sorry, 0 to the power of 0. And we can't evaluate that. That's a math error, that's undefined. Okay, so in fact, we need to look at the limit as x approaches 0. So we could try putting in numbers here. We could try putting in 0.1 to the power of 0.1 or something like that. And I don't think that would really get us anywhere because these seem like kind of small numbers, but we don't really know what happens when we use the 10th root on 0.1. So it's going to be a little bit difficult to work that out. So instead, what I'd like to do is try to use the logarithm on both sides. And this time I'm going to use logarithm to the base 10 because it's easier to work with. So if I use log to the base 10 of y on this side, I'll get log to the base 10 of x to the x. And in fact, it's a logarithm rule that any exponent I can bring to the front. I can make it multiplied by x instead of to the power of x. So I can now write this as x times log to the base 10 of x. Okay, something like that. And I can think about some values of x that I could put in here. So I could start by trying, I don't know, x equals 10 to the minus 3, 1,000th. Okay, and log to the base 10 of 10 to the minus 3, well, that's just minus 3. Okay, and the x here would still be just times 10 to the minus 3. Okay, so that's a pretty small number. We're saying log to the base 10 of y is this quite small number. But what about if I use an even smaller x now? Let's just say, in general, it's going to be 10 to the minus n, and I can think about making n bigger and bigger and bigger to make this x smaller and smaller. Well, by the same logic, it's going to be minus n times 10 to the minus n. Okay, so if I multiply n by 10, if I make n 10 times bigger, this number at the front will get 10 times bigger in size. It's still negative. But this exponent will also get 10 times bigger in size, and it's negative. So that would be equivalent to dividing by 1 divided by many, many zeros, right? By 10 times more zeros than you previously had. Okay. So, in fact, this is always going to decrease, okay, as n gets bigger and as x gets smaller. Okay, so it's going to decrease to 0 effectively. And we know this is actually equal to log to the base 10 of y. So if we put everything to the power of 10 here, we get rid of this log to the base 10 on the y. And we end up getting y is equal to 10 to the minus n times 10 to the minus n. Okay, this number up here, as x gets smaller and smaller, as x approaches 0, that approaches 0, as we said earlier. So 10 to the power of 0, that's just 1. Okay, so our limit is going to be at 1, and I'm going to put it somewhere here. Okay, so again, using an open circle instead of a dot, because you can't actually evaluate it at this point. So that's just 1. So it does kind of look like e to the x because it does start from here. But if we now think about some values that we could put in, we can put in what is x when it's equal to 1. Well, 1 to the power of 1 is also 1. So that is definitely a point that we're interested in because it shows that there must be some sort of behavior in this gap that is not increasing. So it's not always an increasing function. And in fact, if you think about x equals 1/2, you have a half to the power of a half. Well, that's just 1 over root 2, and I think root 2 is about 1.4, so 1 divided by 1.4, that's less than 1. That's somewhere, let's say, here. Okay, so we'd expect to have a curve that actually goes down and then goes up. And from this point, yes, you can say it's a rapidly increasing function. We'll talk about what happens for negative x in a minute. So let's put a y and an x label on these axes. And something they might ask you to do is to find the coordinates of this stationary point, of this minima. So to do that, you would have to differentiate y equals x to the x. And as I've mentioned, this is probably implicit differentiation is the best method here. So we could take the natural logarithm this side of both sides, this time of both sides. So that would be x ln x on the right and ln y on the left. Now we can't really differentiate ln y with respect to x straight away, so we're going to differentiate it implicitly. That will give us 1 over y times dy dx. Okay. On the right hand side here, we're going to use the chain rule. So, not the chain rule, the product rule. If I first differentiate x, I just get ln x times 1. Then if I differentiate ln x, I get 1 over x times x, which is just 1. Okay? So writing this as dy dx as a function of x, I just need to multiply by y, and as we said at the start, y equals x to the x. So this is going to be x to the x multiplied by ln x plus 1. Now, if this is a stationary point, the gradient there should be 0, so we can set this equal to 0. And x to the x, so far we don't know that it ever equals 0. Okay, so we'll discuss what happens for negative x in a minute, but certainly positive x, we're fairly sure it's never going to equal 0. So instead, let's look at ln x plus 1. Can that ever be equal to 0? Yeah, it can. So when ln x is equal to negative 1, this is a stationary point. This has 0 gradient. So we can put everything to the power of e here and just say that x is equal to e to the negative 1. This is 1 over e. Okay, I think that's about 0.37 or something like that. So this is 1 over e here. Okay, great. And that's our stationary point. If we want to know the y-coordinate of this, we just need to sub it in. So we'd have, in fact, 1 over e to the power of 1 over e. Not really sure if there's a better way of writing this. I guess we could call it e to the negative 1 to the power of e to the negative 1. Then you can multiply these, I suppose, and just say that that's equal to e to the negative e to the negative 1. And again, I think you can multiply again and just say that this is, can you do that? You can't say it's just e to the e because you can't multiply in by that negative 1. That would not be the same. So in fact, this is e to the negative 1 negative. So yeah, you can't multiply by this negative number here. Okay. So I would put this in brackets. I'd say it's e to the minus 1 over e, something like that. That would be good. Okay. Does that make sense? So let me just think about this for a second. If I evaluate this, that is in fact 1 over e to the 1 over e. And that makes sense, doesn't it? Yeah. So this is the eth root of e, okay? And that is going to be a number bigger than 1? Yes, I think so. Because if you had 1 times itself, e many times, then you just get up to 1. So it's going to be something a little bit bigger than 1 down here. Yeah, that makes sense. Okay, great. So that's where our minima is. Let's now look at the negative values. We can talk about what happens for negative numbers. So let's think about fractional values and a negative power. So if we said we had any fraction, a over b, let's make it a negative a over b. And then you'll have a negative a over b here. You can get rid of the negative sign just by flipping the inside. Just call it b over a minus, to the, then we call it the bth root, and then multiply by a. Okay. So does this work? Does this make sense at all? So the bth root of a negative number, that will in fact be an imaginary number. So we can't really plot it on an xy grid like this, on an xy diagram. So that doesn't work for fractional values, but perhaps it does work for whole number values. And I think sort of straight away you can see that that would work. For instance, -1 to the power of -1, well, that's just 1 over -1, so that's just equal to -1. All right. So let me plot that. If I put a -1 here, then it's at -1. Oops, we want to put that there, -1. So there's 1 point. What about -2? Well, that would be 1 over. That would be 1 over -2 squared, which in fact would be a quarter. So at -2, you have quarter value, and then at -3, I think you're going to have minus a 27th. Okay, minus a 27th value, and it's going to keep doing that for all of the whole numbers. It'll flit either side of the x-axis, getting smaller and smaller. Okay, so that's how we draw the graph of y equals x to the x. It's not defined for fractional negative values. It's also not defined for 0, but it is defined for integer negative values and for all the real values greater than 0. And you're right, it is an increasing function, but only after the point 1 over e. Before that, it is in fact decreasing. Okay, thanks.